Okay, let's unpack this. We are diving deep today into what might be the most mission-critical decision in all of bioprocessing, and that is selecting the feeding strategy. If you've ever operated a bioreactor, you know this tension. You're trying to keep your cellular machinery, maximally productive, but you're also trying to avoid all the things that make them cranky. Too much sugar, for instance, can lead to stress, toxicity, and ultimately a useless product. So our mission here is to give you a high-speed, high-fidelity shortcut through that whole complex decision tree that process engineers use. This isn't just about picking batch, fed batch, or continuous. The ultimate goal here is ensuring you get a stable, high-quality product. It doesn't matter if it's a therapeutic protein or a complex small molecule. You have to actively steer the organism away from its inherent, well, its bad habits.
Yeah.
We've distilled your sources down to a really powerful four-step framework for choosing this strategy. It's logical, and it forces you to start right where you should, which is with the biology. We'll classify the organism and product, then map the physical engineering constraints, choose the base operation mode, and then, and this is the most critical part, we select the precise control philosophy for the feed. You simply can't pick a pumping speed until you understand the organism's metabolic personality.
That is the crucial starting point. I mean, before any hardware is even commissioned, before a single pump is set, step one is classifying that cell. We need to identify really 4 core factors that define its metabolic strategy. The first question is fundamental. Is the product formation growth associated or non-growth associated?
Okay, so are you making the product while the cells are growing, or do you have to wait until after they grow?
Exactly. If it's growth associated, the product flux just tracks the growth rate, mu. Think of primary metabolites, something like lactic acid. In that case, high growth is your strategy. But if it's non-growth associated, and this is typical for so many complex biologics, secondary metabolites, you absolutely must decouple growth from production.
So you build the factory first, then you flip the switch to actually make the goods.
That's a perfect way to put it. And that decision immediately steers you away from a simple batch operation.
That makes perfect sense. Okay, now for the cellular temperament. The second question you mentioned was about inhibition and overflow.
And this is where so many processes fail. Does the organism crash, or does it inhibit at high substrate concentrations? More importantly, does it exhibit what we call problematic overflow metabolism?
Overflow.
Yeah. So when highly aerobic organisms like E. coli are fed glucose too quickly, they can't process it all through respiration. So they shunt the excess carbon through fermentation pathways.
And that creates toxic byproducts, right? Like acetate.
Exactly, acetate. We use the term QS, the specific substrate consumption rate, to measure this. So if you know your organism overflows dramatically when that QS gets too high, your feeding strategy must, by its very design, cap that rate.
Wow, that's a massive implication. I mean, if a cell makes toxic waste when it eats too fast, the feed pump effectively becomes a poison delivery system if we run it too aggressively.
That is exactly right. And tied directly to that is the third question, catabolite repression. For many organisms, especially in industrial fermentation, high residual glucose will strongly repress key metabolic pathways.
Often the very pathways you need for your product.
Often the very respiratory pathways or secondary metabolic routes that you need for product formation.
Yes.
Yes. So if you have strong repression, you just cannot afford to have residual substrate floating around. The cell will literally shut down the valuable, energy-intensive machinery you're counting on.
So tightly controlled, low substrate becomes a mandatory goal.
It has to be.
And the final piece of the biological puzzle is the process type itself. Are we talking aerobic, microaerobic, or anaerobic?
And aerobic processes are inherently the most challenging. They just are.
Why is that?
Because they become constrained by physics very, very quickly. At scale, the ability to transfer oxygen from the gas bubbles into the liquid broth, what we call Ki, that is the ultimate bottleneck.
Yeah.
And since feeding directly dictates the cell's oxygen uptake rate, or ORR, these aerobic processes are just exquisitely sensitive to the feeding strategy. The feed rate becomes synonymous with the OUR.
So we've characterized the cell's personality. If it's temperamental, needs low sugar, and needs a ton of oxygen, we already know we're looking at some kind of high control solution. But that high control solution still has to fit inside the physical box we built. So let's pivot to step 2. Mapping the engineering constraints. What are the hard boundaries here?
Right. So we're moving from metabolism to mechanical limits. The hard boundaries are defined by the hardware at the largest scale you intend to run. You have to know your absolute maximums. The primary constraints, especially in aerobic fermentation, are always oxygen transfer and cooling.
Right.
Your oxygen transfer capacity is just the maximum OUR that your Kela will allow. If the cell demand exceeds this, you starve the culture. It's that simple. And, the second law of thermodynamics tells us that all that metabolic activity generates heat. So your maximum cooling capacity dictates the volumetric heat release you can tolerate before the batch just overheats.
And we can't forget about how soupy the broth gets, the rheology.
That is the third major constraint, broth rheology.
Hmm.
If your strain is filamentous or the cell density gets so high that the broth becomes really viscous, mixing suffers.
And if mixing suffers, mass transfer suffers.
Exactly. And your Kala drops significantly, which lowers your OER ceiling. So you might have a brilliant feed strategy on paper, but if you can't stir the tank electively, localized limitations will still lead to overflow and stress.
The consequence of that selection is pretty stark. I mean, if oxygen and heat removal are tight, and if your product demands these long, sterile campaigns, those physical constraints immediately favor fed batch over classical continuous systems.
They do.
You have to be able to actively throttle the metabolism just to stay within the physical limits of the vessel.
Yeah, the classical chemostat, which can run continuously for weeks, is just penalized by a higher contamination risk. Plus, you often can't achieve the necessary high cell densities while managing OUR and heat efficiently at a massive scale. Fed batch gives you that crucial active capping.
Okay, so we know the cell's demands, we know the reactor's limits. Now we hit step 3, choosing the base operation mode. Fed batch has been sort of hinted at as the default, but let's be really intentional about this choice.
It needs that intentionality. Let's cover the simple case first. You only choose batch, where you load everything up front, if simplicity and low cost outweigh the need for tight control.
So when is that suitable?
It's suitable if the product is purely growth-associated, and most importantly, if the overflow is either benign or actually desired. Think about high-sugar anaerobic fermentations for bulk products like beer or lactic acid. You want that initial high substrate load to push rapid fermentative metabolism.
But if fed batch is mandatory for maintaining product quality and hitting those high titers, what kind of costs, either capital or operational, are we accepting by making that the mandatory choice?
Well, we're accepting complexity, primarily. Fed batch requires continuous sterility management for the feed line. It needs real-time monitoring and a much more complex control system than a simple batch run.
So you're trading simplicity for control.
You're trading capital expenditure and operational simplicity for metabolic control and, hopefully, increased product quality. Fed batch becomes mandatory when high cell density is required, or if you must decouple growth and production, or if the organism is prone to those bad habits we talked about, acetate formation, inhibition, repression at high substrate. It's really the only way to actively cap the QS below that toxicity or repression threshold. It is the essential compromise of modern bioprocessing.
So what about continuous or hybrid systems? I mean, if it offers these theoretical advantages in consistency and volume throughput, why isn't it the industry's starting point?
Because it's an optimization, not a guarantee. You really only graduate to continuous if 3 factors align. First, your strain has to have extremely high genomic stability. You can't have cheater cells taking over during multi-month campaigns, which is a very real risk.
Okay.
Second, you must have steady product demand that actually warrants 24/7 operation. And third, you need regulatory comfort with these long campaigns, which carry higher, though manageable risks of low-level long-term contamination events.
So for most new biologics, fed batch is just the safer, more robust regulatory path.
It is.
That locks in the mode choice. So for you listening, assuming we've landed on the industry standard, fed batch, the next step is the real technical hurdle. Step 4, selecting the control philosophy. Once we've decided we need to feed, we have to decide how the brain of the bioreactor is going to control that feed rate.
And this really defines your success.
Yeah.
We have to decide what the intentional regime for the residual substrate is. Do we target, say, strict carbon limitation, keeping residual sugar near zero to minimize repression and maximize respiratory yield?
Or maybe something else.
Or perhaps mild carbon excess, which would allow for rapid biomass buildup in a growth phase. Or in some cases, you want intentional excess because you actually want the fermentative overflow to produce your final molecule.
And that intention guides the choice of control philosophy, which we can sort of categorize by complexity. So let's start with the simplest. Level 1, predefined feeds. This would include things like simple constant or linear feeds. They're easy, but they only work for extremely forgiving organisms or when you're operating way below your system limits. The more sophisticated level 1 option is the exponential feed. It's designed mathematically to maintain a constant growth rate, mu, and a constant QS. That sounds ideal in theory.
It is ideal in theory, but the fatal flaw of the exponential feed is scale-up. Because the feed rate increases exponentially, it guarantees that at some point, the theoretical RUR requirement of the culture will exceed the maximum RUR capacity, the coli, of the vessel.
It's a guaranteed collision.
It is, and the sources really stress this. You have to calculate the exact moment that limit is hit, and then you derate your exponent to ensure the feed rate never pushes the OUR beyond your safe ceiling. Failure to do that leads to a guaranteed batch crash.
So relying purely on a mathematical model is just too risky because real-world physics always intervenes. This must be why level 2 simple feedback strategies is so powerful it lets the reactor self-adjust.
Precisely. Level 2 uses the cell culture itself as the sensor. The workhorse here is the diostat.
The DOS.
Instead of relying on a time-based schedule, the diostat uses the dissolved oxygen level as a real-time proxy for the cell's metabolic activity. So if the cells suddenly start eating faster, maybe because of feedstock variability or some genetic shift, their RUR spikes and the DO level in the tank drops.
And the system responds.
The diostat detects that drop and automatically throttles the feed pump back, preventing the onset of oxygen limitation and overflow. And conversely, if the cells slow down, the DO rises and the feed ramps up. It's an automatic protective ceiling against the organism's bad habits. And it's especially useful when oxygen limitation is your primary scale-up risk.
That is fascinating. It's essentially letting the cells tell the pump exactly how hungry they are in real time, with the DO probe as the mediator. What about other level 2 metrics?
Well, we also use pH stat tracking acid or base addition rate, which is a great indicator of a metabolic shift. For example, acid production from fermentation means overflow.
Right.
Or RQ stat, which tracks the respiratory quotient from the off-gas. These are all elegant, simple ways to protect the badge without needing really complex modeling.
And then finally, the ultimate technical ambition. Level 3, the advanced model-based strategies. If a diostat is so great, why would we ever invest in something more complex?
Level 3 is really reserved for the highest value, high-risk processes where the cost of a batch failure justifies an immense investment in instrumentation and validation. These strategies require real-time biomass sensors, robust soft sensors, and comprehensive predictive models.
So what are some examples?
Well, there's the MUSTAT, which uses real-time biomass measurements to calculate and maintain a specific optimized growth rate. Or Model Predictive Control, MPC, which can simultaneously constrain multiple variables, hour heat generation QS, and predict the optimal feed strategy hours into the future.
But the complexity is huge.
The complexity, the maintenance, the validation required, it all means you have to have a strong digital infrastructure and a highly specialized team to make it work.
We mentioned scale-up risks earlier, but I want to emphasize one point from the sources. The difference between local and bulk DO. Why can an aggressive feed lead to failure even when the bulk DO probe reads just fine?
That's because of mixing limitations. In large vessels, the bulk DO probe might be located far from the feed injection point. So an aggressive exponential feed can create these local zones of high substrate concentration, leading to immediate localized oxygen starvation and overflow metabolism right near the impeller, even while the bulk fluid looks okay. And that localized stress generates toxins that still ruin the product.
So the rule is to build in a safety margin.
The critical rule is always to choose a level 2 or 3 strategy that builds in a safety margin. A ceiling may be 20 to 30% below your maximum RUR limit at top scale.
That safety margin is priceless.
Yeah.
Okay, let's bring all this home now and connect these technical decisions directly to what really matters. Product quality.
Let's start with a classic example. Using E. coli to produce a therapeutic recombinant protein. If we just ignore the framework and use a high glucose batch or some overly aggressive fixed feed, the risk is acetate overflow.
The toxic byproduct.
Right, and acetate is a severe stressor. The quality impact isn't just a lower yield, it's protein misfolding. Instead of the product you want, the cell starts producing these insoluble aggregates we call inclusion bodies.
Which is a nightmare for purification.
It massively complicates downstream purification, drives up costs, and reduces the final purity and consistency from batch to batch.
So what's the quality-focused solution then?
Strict carbon-limited fed batch. We apply the framework. We use an exponential feed initially to get high cell density. Then we have an immediate transition to a tight level 2 or level 3 control like a diostat or a MUSTAT during the protein induction phase. This keeps residual glucose near zero. It reduces acetate formation by orders of magnitude, and it results in a more consistent, soluble, higher quality product profile.
The yeast example is fantastic because it really shows this dual personality of a single organism based entirely on the product goal. Let's talk about Crabtree-positive yeast.
Right. So if your goal is bulk ethanol production, we'll call that scenario A overflow, is the entire strategy. You choose batch or high sugar fed batch, and you just push that fermentative metabolism. But if we use that exact same yeast to produce a secreted protein scenario, B, the overflow, the ethanol, is now a toxic byproduct.
So the solution has to be completely inverted.
Absolutely. You have to implement a tightly glucose-limited fed batch, staying well below the Crabtree effect threshold. And the quality implication here is profound. When the cells are happy and unstressed under that carbon limitation, they produce dramatically lower levels of stress-induced proteases.
And those proteases are bad news.
They're notorious for clipping and degrading the secreted therapeutic protein product. So the quality-aware strategy leads to higher integrity and higher stability of the final molecule.
Let's touch on the complexity of modern feedstocks. Things like lignocellulosic hydrolysates, waste streams that are cheap but incredibly variable.
This is a massive challenge in fermentation today. These feeds contain mixed sugars and highly variable levels of metabolic inhibitors, like furans and phenolics. So if you use a simple fixed feed profile, the variability in that feedstock is just going to translate into wildly variable QS because the inhibitors cause these sudden, unpredictable shifts in metabolic activity and growth arrest.
And the resulting quality failure from that.
You get wild batch-to-batch variability in the purity and concentration of your final target molecule. Maybe it's an organic acid profile. The simple fixed feed just fails because the input is too inconsistent.
So the solution has to be feedback control.
The quality-aware solution must be a fed batch with quality-aware control. After some minimal pre-treatment, you have to rely on a feedback loop like a robust diostat or even substrate sensors if they're available to automatically compensate for those variable inhibitors, ensuring the organism only ever sees the sugar at a rate it can safely handle.
This all brings us back to a unifying logic, doesn't it?
It does. The feeding strategy is the primary tool we use to force the cells to operate in this narrow, highly controlled metabolic corridor. This corridor is where the product is formed efficiently and, most importantly, cleanly. Any deviation, and it's usually caused by an incorrect feed rate, creates unwanted side products, toxic acids, misfolded proteins, degradation, or just low-quality product. That means you have to do astronomically expensive downstream purification.
So to summarize the framework we've been through.
We covered the mandatory framework. You classify the product in the organism, you
Yeah.
map the engineering constraints, you choose the base mode, and then you select the right control philosophy.
We started with the inner workings of the cell. We layered on the unforgiving physics of oxygen and heat transfer. And then we applied control logic to handle the inevitable variability and unpredictability of the real world. So here is the final provocative thought for you. The most effective feeding strategy is never found in a generic textbook or some starting recipe. It is found by picking the mode and the feed logic that keep the organism away from its bad habits, overflow, repression, stress, for the substrate you actually have and at the largest scale you actually run. That highly specific, tailored level of control is the fundamental difference between simply running a high-yield process and consistently producing a reliable, high-quality product. Thank you for sharing your sources for this deep dive.